Okay, our next speaker is Wen. Wen is a third-year PhD student from Tsinghua University, who is supervised by Professor Yunxin Liu and Professor Yuanchun Li. His research interests include personal mobile agent and edge AI. So he's going to share their work titled AutoDroid-V2, boosting SLM-based GUI agents with code generation. So please join me in welcoming Wen.
And I'd like to present our work, AutoDroid-V2, boosting SLM-based GUI agents via code generation. So I'd like to first acknowledge our team at Tsinghua University, and we are a team dedicated to advanced mobile agent research, and we have brought a series of works on the mobile agents. And we are open to all sorts of the collaboration and suggestions. So in the past few months, we have witnessed the revolutions of SLM-based GUI agents. So we have Cloud and OpenAI, they have brought many fantastic works and products on the UI agents. And we have many great teams from all around the world, and we are all doing the UI agent works. So the UI agent is that for user tasks described in their voice or their natural language, and the agent should automatically bring the tasks into real world in their smartphones or IoT devices. We can model the problem of UI agent into task automation, where the input is a user query described in natural language, such as remind me to do laundry on Sunday. And the output is a series of actions to complete the task. The actions are like clicking, inputting, scrolling, and so on. And the actions, we can automatically send them to their smartphones by Android Debug Bridge or accessibility service. The difficulties in this problem is the task understanding. We have to understand all forms of user tasks, and we have to plan for many complex tasks. And we also need to ground each UI action into the screenshot, so it can be very difficult. And before the emergence of large language models, many products have adopted the template-based methods, where the developers or the users has to predefine their task based on the templates. They have to describe the workflow of their task based on JavaScript or XML and so on. And so the limitation of this method can be very obvious. So we have to write a lot of code for each task we want to support, and the scalability of this method can be very poor. So the research teams have brought many learning-based methods to deal with the limitations of the template-based methods. We can use supervised learning or reinforcement learning to train a deep neural network to learn the mapping from the task and the UI state to the UI action to solve this task. But this method can be very limited too, because we have to collect a lot of UI actions and task pairs to train a deep neural network. And we have to deploy every single reward function for the tasks for reinforcement learning. So after the emergence of the large language models, we have brought many large language model-based methods for mobile task automation. The key insight is that the large language models are trained on very large training data, so they have a common sense knowledge of how the users use the mobile phones. So we don't need a lot of training data or reward functions to train the large language models. We only need a very small portion of the training data, or we even don't need to train the large language models. So we have brought many early work, AutoDroid-V1 in MobiCom 2024, and the mapping is that for user input, we can make a prompt based on this input, and we can also insert the UI action and all the UI screens in the prompt and send it to the large language models deployed in the cloud. And so that the cloud large language models, based on this task and the prompt, they can give a UI action and send it back to the smartphone. And then it can iteratively do this until it thinks that the task is done. So we can call it as the stepwise method. By stepwise method, we mean that it has to, the large language models has to be called at every single UI step. For a task, we may need to interact with more than 10 UI states, and then the large language model, the LLM is called for 10 times for this task. So the latency of each task can be very high. We may need more than 10 minutes for one single UI task. And also, as we need to send the screenshot and the UI state to the cloud, so the privacy and security risks are concerned too. And also, we need to call large language models for many times, so the user side traffic consumption and the server side centralized serving costs can be very high too. So in order to solve the above question, the research teams have brought many small language model-based methods to solve it. Ideally, the small language models are the models smaller than 10 billion parameters, and we can deploy them in your smartphone. So we don't need to connect to the cloud, ideally. But for these methods, there are also many limitations. The first is the accuracy method, because the capabilities of small language models are still far from their cloud-based methods, because the limited of their parameters and the trained data, so they can perform very poorly for the UI task automation. And the second is the efficiency. So it's still stepwise method. So we have to call small language model at each step to compute the UI action at your smartphone. So it's still very computationally intensive. So what we are thinking about is that, can we convert the stepwise method into a script-based method? So we just need to call the small language model or the large language models for one time, and it can generate a whole script, a whole solution for this task. And then we just need to execute this script on your smartphone without the need of calling large language models. The insight mainly comes from that small language models can be trained to have a unique strength in coding. So this is only because they are trained on massive training data, the code data from GitHub. So small language models, although they are very poor at common sense tasks, they are trained to have a good sense of coding. But even so, for this script-based method UI agents, it still has many difficulties. The first is that for script-based GUI, to understand every GUI elements in this app to complete a random task for the user. And we can say in the right side that for even one single app, it has many UI screens to understand. And the second is the dynamic nature of mobile apps. So we have many GUI agent states in one app, and for even one UI state, it has many variants. And this is only because that the UI elements can change in text, in location, or in size. So in the above, we have 5 different UI screenshots, but they are only for one UI state. And also, contrast to our instinct. So for one UI screen, and we perform the same UI action on it, it can even lead to different UI states based on the status of this app. So the third is a limited context length and the computational resources. So when we deploy the small language model on your smartphone, it has to be very lightweight and it has to be compute very fast. So we are here to propose AutoDroid-V2 to solve the above difficulties. The core idea behind this AutoDroid-V2 is to automatically construct an informative app document. And use this app document, we can get the large language models or small language models to generate multi-step domain-specific device control scripts. The start point of this method is the exploring history. The exploring history can be obtained by a random explorer or the user using app history. And then, based on this informative exploring history, we can build a concise and informative app document. And use this document, we can generate large scale of synthetic data. The data are the task, multi-step code pairs. Then we can verify these data based on the simulators or the smartphones. And after that, we can use this data set to fine-tune a local large language model, just as small language model. Then after, we can deploy the local language model in your smartphone. And for a random user task, we can query the local language model and generate a multi-step code and automatically execute this code on your smartphone. So first, let me talk about the automated app document generation. We generate the app document based on two-stage analyzing. The first is how to group the UI states, because for each UI state, as mentioned above, we have many variants, and we have to detect in the exploring history which are the variants of one UI state, and then we can group them. We can group them by layout similarity and functionality similarity. And after that, we can extract the UI elements in this UI state. So this is an example of an app document for two UI states, one lead to another. We can summarize it in the app document and get all the UI elements. And after we get the app document, we can generate over 1,000 simulated tasks for each app. We generate the task by sampling some element subsets and ask large language models to generate the tasks. After that, for each task in these simulated tasks, we can ask large language model to generate a script to complete the task. But as we all know, the large language models can have a serious problem of hallucination. So the script might be wrong. We have to validate this script based on your smartphone or an emulator. So after we get the script, we can use a domain-specific Python code executor to execute the script on their smartphone and get an execution trace. And if the Python code executor throws an error, we can query large language model to generate the script again. So this is a tree-based script search. We can search until the script is executable. After the script is executable, we can use large language model-based judge to judge if this script is correct for the task. And if it's correct, we can add it to the training data. If not, we can go the tree-based script search again. So finally, we go to the online part. So as we get the task script data, we can fine-tune the local language model to do the task automation. And after the local language model is trained, we can deploy it in your smartphone, and given a task, we can make a query, a prompt to the local language model again, and we can generate this code now for your random task. If at executing the task, there throws an error, we can go again and get the code generated query again and get the script. And also, for the long prompt, we have to include the GUI elements and the whole app document in the prompt to let local language model know about how to complete the task. So we can use KV cache to reuse the static app document, and this can reduce the language model pre-filled latency largely. So this is our method, and we evaluate our method on two well-known datasets. The first is Joy Task Benchmark, which we proposed in AutoDroid-V2, and it has more than 150 tasks with app explorer history. And the other is AITW subset with 68 tasks supported by Llama Touch environment. And we compare two very strong baselines, and our method achieves the highest success rate and reversed redundancy ratio. And for the latencies, our overhead are largely saved by KV cache reusing and the script-based methods. So the conclusion is that the script-based methods has a potential to boost the LLM or SLM-based GUI agents. But implementing a script-based GUI agent is hard. First is the complexity of the mobile apps, and the second is the efficiency problems. So AutoDroid-V2 automatically constructs an informative app document and guides the SLMs to generate domain-specific device control scripts. But there still exist many challenges for these GUI agents. For example, how can we support multi-app or multimodal tasks by providing more scalable app documents? And how to efficiently deal with app updates? And how to deal with highly dynamic user interfaces such as web search engines and games? So that's all. Thank you.
Okay, thanks Haowen for great talk. Now we have a couple minutes for Q&A sessions.
Very interesting work, and this is Le Min from Hong Kong PolyU. I have a question that, so for each app, you need to go through the offline phase to construct a comprehensive document for that app. Yeah. Is that right?
Yes.
Okay, so so have you ever considered that what if the app is updated? You know that currently our apps are continuously updating, so the GUI may change. Yeah.
Yeah, it's in the limitations.
Okay.
And yes, we have thought about it because for updates, there are only a small portion of the functionalities of the app will be updated. So we don't need to change the entire app document. And for the fine-tuning process, we can only add the newly generated tasks. So we think that it won't cost a lot to support the app updating.
Okay, and another question is, so you mentioned that when the generated script cannot be executed, you need to repeatedly generate new scripts until it can success. So yeah. I'm curious that what is the probability of that case?
For our experiments, we found that only about 10% of the script can be corrected by this regeneration. Most of the errors can't be handled. We observe that. So it's also a limitation. And we think that this is mainly because that for the fine-tuned data, we don't include the regeneration data pairs. So maybe the fine-tuned local language model don't have this capability. So we are still working on that. So the incoming maybe in V3 or the following works.
Okay, I see. And the last question is that so during the RAG process, let's say what if the task proposed by the user is not matched with any of the case in the RAG dataset, because the user requirements are very diverse. even if you have a large amount of synthesized data. Yeah.
Yeah. So the first solution is that the exploration data should be very general and should cover almost every UI state. And for the situations that it doesn't cover a UI state, because for this UI state, we also include the UI elements and also the current UI elements in this prompt. And if it throws an error because it doesn't match any of the elements, it can get the current UI state and include it in the prompt and regenerate the script.
Okay, I see. Thank you very much.
Yeah, thank you.
Thank you for the talk. I'm Yunxin from Yunxin University. I have a question. Before going to the question, I wanted to make sure that if I'm understanding correctly. You said that you're training an LLM to kind of memorize the scene states. Is it correct?
Sorry, memorize what?
So if I understand correctly, that you kind of get the scene state that you explored, the program explored,
yeah,
and use that data set to fine-tune the local LLM. Is that correct?
Yes.
So it's kind of memorizing the state.
Yes.
Is that correct? So if that is a true thing, then kind of fine-tuning LLM in local devices is kind of a hard problem, I think, still.
Yeah.
So did you kind of try to use that data set to just like don't fine-tune the LLM and just use that data set to kind of do the process? Because,
Yeah, we have tried it. So, so the problem is that the small language models that can be deployed in your smartphone, they have very poor context length.
Yeah,
so they don't.
That's correct.
They can't include all the prompt in your context. So after fine-tune, you can only generate a little portion of the UI elements, and it can still summarize, memorize some of the. Elements.
So just fine-tuning the LLM was the resolving the problem of the context length.
Yeah. Also the poor scalability of the small language models.
Okay. Thank you.
Hi. Thanks for the great presentation. I have a question regarding the error correction stage for both your offline and online pipeline. So when the code executor finds an error, and it will just query the LLM again to generate the new code.
Yeah.
But I have a question for some of the times the code can also go wrong, but not in the way that it throws an error, but actually it passes the compilation and it can actually run, but it runs in a wrong way.
Yeah.
So how do you deal with this situation?
Okay, so for the online state, most of the UI agents now can't achieve a very high task completion rate. That means that most of the tasks can't be completed by the UI agents now. So for our method, for other UI agents, it's all the same. So we can't guarantee that each UI task can be completed 100%. So for the online, we can see that we try to match the tasks, but we can't guarantee that if it goes to a wrong way. And for the offline, so this is the part. So if an execution trace doesn't match the task, the large language model's judger can judge it whether it is good, and if it's good, it's added. But if it's not, it can fail through an error. So,
thanks for your answer.
Yeah, thank you.
Hi, very nice talk. This is Bo Yuanyang from University of Pittsburgh. And I'm actually interested in your online phase. Like you mentioned that you are using the task and script pairs to do a fine-tuning for the online small language model. So I'm actually interested that have you considered these things where new apps are being installed? Are you trying to refine-tune the small language model incrementally, or are you planning to just do a fine-tuning from scratch? Or if you are doing that incrementally, will there be issues like when later apps are being installed have been fine-tuned, and in that case, the earlier knowledge could be forgotten by the small language model due to the size of it? Do you have any data for that?
Yeah, for our experiments, we have found that fine-tuning on new apps, it does not hurt the capabilities of the former apps, because we found that maybe the UI elements are still a small portion of the pre-training data. So it can still be memorized by the parameters of the small language models. And I think it's also a great question about the application of our method. So ideally, we want to build a local language model for each app. So we want the app developer to fine-tune this large language model and for their app. And so when deployed, it just sends the local language model to our smartphone.
So the model size could be an issue. So what is a typical small language model size in your case?
We have done experiments on parameters of 3 billion and 7 billion and 8 billion. Yeah. So, but now we have witnessed a lot of even smaller, like 0.5 billion. They can do much better than the former 7 billion or 8 billion. So,
yes, thank you.
Thank you.
Hi, nice talk. Do you mind going back to how you generate the app document?
Yeah. This?
Yeah, okay. So you may have covered this, but my question is more like, so let's say you have in your app,
Yeah.
you have a state where you have to pass like a login screen to access like a bunch of functionality.
Yeah.
Do you like rely on, in this case, do you rely on like collected data from users interacting with the app on their own to like inform this state, or do you have like some way to like give dummy data, or how do you get around that situation?
Yeah. Ideally, so for each app, when they are developed by the developers, they have to test on them, and you have a lot of test users, and they also use a lot of automatic test tools like Droidbot or Appium to test these apps, and we can collect the exploring history on both the automatic testing tools and the test users.
Okay, so this is like something that would be good for including in the loop while you're developing, and then this can be like distributed along with your app in the App Store?
Yeah, we think that the offline should be done when the developers
I see.
develop the app.
Cool, thank you.
Thank you very much.
Okay, let's thanks again for Haowen for the great presentation, or also thanks our audience for raising many good questions. So now let's move on to our final speaker.